Now that we know how to solve a first-order recurrence relation, let's take a look at some higher-order homogeneous recurrence relations. This will obviously be a bit more complicated than what we just finished doing because now we have a second-order or third-order recurrence relation where we're dealing with more than just one previous value. We have 2 or 3 or 4 previous values, etc. The more values that you have, obviously, the harder this is going to get. But this page is a good reference, so this might be something that you just take a screenshot of and come back to. Just reference back to it because it's going to be the same steps each time. We're going to go through each of these steps together in the upcoming example, so I'm not going to talk through these 4 steps right now. I'm going to talk through them as we use them. For our first example, I've labeled this as case 1, and I'm just dealing with different cases because of step 3, and when we get to step 3 I'll make that very clear. But step 3 says essentially based on the form of the function, and that's where this will differ from, say, case 2, where we're going to have to use a different form. But let's go ahead and get started on our steps. Step 1 is rewrite whatever your recurrence relation is so that it is equal to 0. Do that first. So as you can see, this is not equal to 0. I am now rewriting it by subtracting 5a sub n minus 1 and adding 6a sub n minus 2 so that I have it equal to 0. Then what we want to do is write a characteristic polynomial. And it's really pretty straightforward, so I've shown several steps, but really typically I'll just go straight here. And what we're doing is we're saying, let's take whatever our subscript is here and turn that into an exponent for r. So a sub n is now r to the n. Minus 5, I'm keeping the minus 5, a sub n minus 1 is now r to the n minus 1. 6, a sub n minus 2, I keep the 6, a sub n minus 2 turns into r to the n minus 2. Then I say, well, what can I factor out of everything? Let's factor out r to the n minus 2. What does that leave me with? The characteristic polynomial. So the easier way is to just say, whatever the lowest one is, this guy, will have essentially r to the 0. The second lowest will have r to the first, etc. It will continue to increase from there. That is the characteristic polynomial. So if I were you, once you put it in the right format, just go straight to the characteristic polynomial. Step 2, and again I've rewritten that characteristic polynomial for you here. We're going to factor. So again, we know how to factor. You are in upper level mathematics. I'm going to assume we all know how to factor. I'm not going to go through that. This factors into r minus 2, r minus 3 equals 0. And then of course we're going to find the roots, which means set r minus 2 equal to 0 to get 2, r minus 3 to equal to 0 to get 3. So I have 2 roots, and notice that the roots are different, and that is what makes it a case 1. We're dealing with different roots. And that will change based on step 3. That will change how we approach step 3. So let's take a look at step 3. We have our roots that are different, and we need to essentially determine the correct form of a sub n. So if we have 2 roots that are different or distinct, then, and you'll see different videos use alpha and beta or lambda 1 and lambda 2. I just like to keep things simple, so I'm just going to use a and b, but it's not incorrect to use alpha and beta and gamma or lambda 1, lambda 2, etc. What we're doing here is we're using the form. If we have different roots, it's going to look like this, and if you'll notice, I'm using the root of 2 and the root of 3 here in my question. I also have my values of a and b, which I don't know the values for a and b yet, but obviously that's going to be what I do in my next step, is solve for a and b. But this is the correct form if I have 2 distinct roots, or even if I had 3 distinct roots. let's say I had a root of 4, then I would have plus c 4 to the n. So you get the idea. It's pretty straightforward. Again, this is for distinct roots. That's case 1. So here's my equation, again, rewritten for you so we don't have to try to memorize things. Then all we're going to do is, and this part's super easy because this is way back to like Algebra 1, we're going to write and solve a system of equations using these initial values. So I'm saying a sub 0 is equal to 1, which is equal to a times 2 to the n, well n obviously is 0, plus b times 3 to the 0. So this equation turns into a times 1, so that's a, plus b times 1, which is b, is equal to 1. Did I do the same thing for a sub 1? A sub 1 is 1, and that's telling me take a times 2 to the first, plus b times 3 to the first. So to rewrite that more simply, I have 2a plus 3b equals 1. So that's the process I went through here to find those two equations. Now I just have a system of equations. So solve using substitution, elimination, whatever method you deem best. So obviously what I did is I took negative 2 times each value in my first equation. I did that so that when I added these two equations together, negative 2a and positive 2a went away. I got b equals negative 1. I took that b value and plugged it back in here. A plus negative 1 equals 1, so a is 2. And then all I did was take this equation and replace a with 2 and b with negative 1. Notice here I ended up with 2 times 2 to the n, so I actually wrote that as 2 to the n plus 1 because really I'm just adding those exponents. And I changed my plus to minus because I was dealing with a negative 1, but this would be my explicit way to write what a sub n is. Keep in mind that it is never a bad idea to check your solution. So how do I check a solution? Well, I would use this formula, which I know is correct because it was given to me at the beginning, to find, say, the next value in the series. So obviously I have a sub 0 is 1, a sub 1 is 1. I'm trying to find a sub 2, so let's do that here. A sub 2 would be 5 times a sub 1 minus 6 times a sub 0 based on this equation. A sub 1 is 1. A sub 0 is 1. So really I end up with 5 minus 6 or negative 1. So I know that my next value should be negative 1. So now the question is, did I do this correctly? Will it also give me negative 1? Well, according to my function, this should be 2 to the 2 plus 1 minus 3 squared. Well, 2 plus 1 is 3, so 2 cubed minus 3 squared, which is 8 minus 9, which is negative 1. And because I got the same thing twice, I know that I am a genius and I did it correctly. Here's a very similar example for you to try on your own. Again, this is a case 1 example, meaning I'm going to end up with two distinct roots, so you're going to use that same form on step 3. Really everything else is exactly the same. Press pause, try all of the parts of this question. When you are ready, press play to see how you did. So again, step 1 is to put everything in the proper order and write the characteristic polynomial. So that means I've got a sub n, I'm subtracting this from each side, I'm subtracting this from each side, so I want this equal to 0. Notice I went straight to the characteristic polynomial in this case, so what I was looking at is this guy is the smallest, a sub n minus 2, so that's r to the 0. The next one up is r to the first, the next one up is r squared. That gave me this characteristic polynomial. That factors quite easily into r minus 3, r plus 2, which means my roots are 3 and negative 2. So that's really step 1 and step 2 together. Step 3 is to use the same format that I used last time, which says I'm really just taking the root to the power of n, each root to the power of n, and a and b are two distinct values. From here, I'm now going to use my initial conditions. So here's my two initial conditions, which means I'm going to get my first equation from here and my second equation from here. So I'm taking this and basically replacing n with 0, which is equal to 1. A sub 0 is 1, which means a times 3 to the 0, and then b times negative 2 to the 0. Reducing that, I come up with this first equation. Then I do the same for a sub 1. So I've got a sub 1, which is equal to 8, is a times 3 to the 1st plus b times negative 2 to the 1st, and that gives me my second equation. Now that I have a simple system of linear equations, I can solve it, substitution or elimination. If you'll notice, I just took everything here times 2, because that gave me 2a plus 2b equals 2, which means when I add these functions together, my b's cancel out. I get 5a equals 10, or a equals 2. I took this equation, replaced a with 2, and found that b was negative 1. So a is 2, b is negative 1. What do I do with those two things? Well, I take this guy and I replace a with 2 and b with negative 1, and then I do whatever simplification is necessary, which really wasn't much. So here is my final solution. Now that we've done a couple of case 1 examples, let's take a look at a case 2 example. And again, the only thing that's going to change with the case 2 example is that when I find my roots, I'm going to find that I have the same root, and we'll see how that changes step 3. But the good news is everything else is really the same. So just as we did before, the first step is to put everything into one side of the equation and set it equal to 0. So I have a sub n minus 6 a sub n minus 1 plus 9 a sub n minus 2 equals 0. Turn that into a characteristic polynomial, r squared minus 6r plus 9 equals 0. Factor r minus 3 equals 0, or r minus 3 squared equals 0. And notice that means that my root is positive 3, but it's a multiplicity of 2. It's a double root. It's the same root 2 times. So instead of using a sub n is equal to a times the first root to the n plus b times the second root to the n, we have to change it up a little bit because this was case 1. So case 2 says, okay, it's almost exactly the same, but what you'll notice is because it was a double root, my second root has to include n. If there was a third root, let's say I had a multiplicity of 3 or a triple root of 3, then it would be c n squared 3 to the n. So we can see what that pattern would be. But right now we're just dealing with 2, so just keep in mind if you have a double root, we're going to be adding n squared, etc. Again, what I said before is everything else will remain the same. So if you were comfortable with case 1, case 2, go at it, finish up this question on your own if you'd like. The next step, of course, is to use my initial conditions. So a sub 0 equals 1. I'm going to go ahead and replace n with 0, which is 1, which means a times 3 to the 0, b times 0 times 3 to the 0, and that leaves me with a equals 1. And then we're using my second initial condition to come up with my second equation, which means a sub 1 equals 2, Since n is 1, I've got a times 3 to the first plus b times 1 times 3 to the first, and again that gives me my second equation. Obviously I've already solved for a without even having to break a sweat. A is 1. How do I find b? Well, obviously I'm just going to take my second equation, replace a with 1, find that 3b is negative 1. This is 3 plus 3b equals 2, subtracted 3 from each side, so 3b equals negative 1, b is negative 1/3. There's my two solutions. Again, just as I did before, I'm taking this guy and replacing a with 1, so it was just 1 times 3 to the n, and b with negative 1/3. So it's okay if I leave my solution just like this. I did a little bit of math magic to clean it up a little bit, because 1/3 is 3 to the negative 1. Notice I just rewrote that as 3 to the n minus 1. And then I factored, because I have 3 to the n minus 1 that I can take out of both. That leaves me with 3 to the n minus 1 times 3 minus n. So either of those that I've put the box around here would be just fine for a solution. Obviously this one's a little bit better, but I'm satisfied right there. Here is another case 2 question for you. So again, it's going to go exactly like this last question. It's just one for you to try on your own. Go ahead and press pause, try this question. When you're ready, press play to see how you did. Again, where I would start is put everything to one side, set it equal to 0, then find the roots, which we find is 2 twice. So remember, the only thing that changes is this step right here where I'm adding the n, as opposed to just a times 2n and b times 2n. I have to add the n because we have a double root. Other than that, everything remains the same. I'm using my initial condition to write my first equation. I'm using my other initial condition to write my second equation. I'm then solving for both a, which I already did, and b, which I did right here. And then again, I'm replacing the values in this format with a and b. I again did some math magic to turn my solution into a little nicer format. But again, this one's okay, or this one's okay, but really that last one is the best okay.